Okay, let's look at the open source implementation 4.4. The function calls are that you the upper layer call the IPQ transmit, and then after the routing is determined, it calls IPQ transmit 2, and then IPQ transmission 2 would call IP fragment if the packet length is larger than the MTU of the link. Okay, so it's a conditional. Conditionally, if the packet length is larger, then this function IP fragment will be called. And then within IP fragment, there's a while loop, which would fragment the original packet into fragments. And the size of the fragment should be set to, except the last one, which will be the remaining byte, but the other fragment will have a size set to the largest multiplicative number of 8, which we have seen in example. If the MTU is 1500, then the largest multiplicative number of 8 will be 1480. And that's a fragmentation, IP fragment. And in IPv4, the fragmentation can be done in a host or in the routers. So the host might fragment the packet if the MTU is too small, and the router might do that too. So the fragmentation can happen anywhere in the host or router, but reassembly can only happen at the destination host, not the router. Okay, if I send a packet from X to Y and traversing to a number of routers, and the host or the router might fragment the packet. But when should I defragment or reassembly? Defragment is the same as reassembly. When should I reassemble the packet back to the original packet? When? The answer is only at the destination host, not in the router. But why not in the router? If I say this is a router 1, router 2, and router 1 fragment the packet in order to pass the link, and then router 2 receive the packet, the fragment, and then can a router do the fragment here? It's better not. But why not? Say, suppose the fragment has been done at the source, but traversed to many routers, and then if you want to do the fragmentation, then the router should become what? Stateful. It would need to queue the fragment. Say if the packet had been chopped into 10 fragments, the router needs to wait for the fragment to come in. And if I queue the 9 fragment and I still miss 1 fragment, I need to wait until I time out. Okay, then the router will need to maintain a lot of buffer and then keep track of this for each fragmented packet. And this is too much overhead for the router. So remember that we want to keep the router simple and fast. So we don't want to do that in the router. So instead of doing reassembly at the router, we do it only at the destination host. But the fragmentation could happen on the host or router, and the source or router. But still, again, if you ask a router to do fragmentation, it is still some overhead, but not as heavy as reassembly. Because for reassembly, you need to wait, right? You need to queue the fragment. But fragmentation is, you don't need to queue, but you still need to do the partition and then construct the packets. So it's still not that good for routers. So what happened in IPv6? In IPv6, it only allows fragmentation at the source host, but not the router. The router are not allowed to do fragmentation because they consider this as an overhead that shouldn't happen on a router. The router should be kept simple. So in so I'm saying in IPv6, fragmentation only at the source host, reassembly at the destination host. Routers are not aware of this. But in IPv4, fragmentation can happen at the source host or the routers, which is different. But similarly, the reassembly would happen only at the destination host. Okay, and then we will see that. I would ask you why. If this is a midterm question, I will ask you why, or final question, I will ask you why. Why in IPv6, fragmentation, reassembly, why in IPv6 and v4, in IPv4 and v6, reassembly is not done at the router, but only at the destination host. And I would ask you why in IPv6, fragmentation is only done at the source, but not the routers. Okay. And now let's look at we have seen the fragmentation. Now let's look at the reassembly. In the reassembly, you will see this function here. This function, inside this function, it will check whether the more bits or offset is set. If there's offset or the more bit is on, then I would go to defragment, which is reassembly. I would do reassembly. If it's not, then it's done. I don't do further processing. But if this is on or this is on, then I do that. And here in reassembly, in IP defragment, I would do this to look up the hash table. IP find. It would look up a hash table. So in order to store the fragment, I use a hash table. They use a hash table. So I check, I do a hash and then check whether I find it in the hash table. If yes, then return the queue, meaning if no, then it means that if I find it in the hash table, meaning this fragment is a fragment of a packet I have seen. See, so this is not the first fragment. This is probably the second, the third fragment of a packet. But if this is the first fragment of a packet, I would not find it in the hash table. Then I would do this. I will create an entry in the hash table, because this is the first fragment of a packet. So if this is the first fragment of a packet, it will go this. I will find it, and I will not find it in the hash table. I will create an entry in the hash table, and then return it to IP find. But if this is not the first fragment of a packet, see, this is second or third fragment of a packet, then I will find it in the hash table, because the first packet have already created an entry. Okay, so here I only want to identify whether this is the first fragment of a packet. So either it's the first fragment or not the first fragment. I already have the entry in the hash table already. So I will queue the fragment. I will queue the fragment. Here I put it in the newly created entry, and here I put it into the matched entry in the queue. And I check whether all fragment is in. All fragments are in. If all fragments are in, then I do reassembly. I do reassembly. If not, then I don't do reassembly. I will just return. I will just return. So by doing this, by maintaining a hash table, I can I only have one hash table for the entire. This is in a destination host. For this host, I only have a hash table for reassembly, and this hash table would contain fragment of many packets. So, for example, perhaps I'm waiting for 5 packets, and some of the and all of the 5 packets have say 4 fragments. Then I would have some fragment for the 5 packets in this single hash table. Okay. So if not all the fragments are in, I would just insert into the queue in the hash table and then return. Until I find all fragments in, I would not do reassembly. Okay, let's look at the next topic. Right after IP, are we still in IP layer? Yes, we are still in the section 4.2. The final topic in section 4.2 is NAT, Network Address Translation. Remember, I said that in the beginning of the class today that we are if the service provider has run out of IP address and cannot allocate more IP addresses, then what it would do is that it would allocate private IP addresses. That's one possibility. So you might get private IP address from a service provider. And another case is that you got public IP address from the service provider, and you are a small company, but internally there is more than one PC, more than one computers need to go onto the internet. So I only got one public IP address, one real IP address from service provider, but internally I have 20 PC. Then I would only give the private IP address to those 20 PCs, and those 20 PCs they would share this public IP address. So that's another possibility. So I'm saying that if you are lucky, still now in Taiwan we can get a real IP address from your service provider, but probably next year or 2 years later you will get private IP address from the service provider. Okay, so you will become invisible, kind of invisible, if you don't run some application, some P2P application to make yourself visible. Otherwise, you will be invisible by holding just a private IP address. And here they define 3 segments, 3 small segments, which are reserved for private IP addresses. And I think some of them are in Class A, Class B, and Class C. See, 10, 172, 192. The first segment is in Class A, and the second segment is Class B, and third segment is Class C. So in Class A, B, C, we have so these 3 segments they fall in Class A, B, and C respectively. Okay, and these 3 segments are reserved for private IP address, and they would not be used on the public internet. So the service provider would not give you I mean, if they give you a real IP address or public IP address, they shouldn't give you address in these 3 segments. Okay. However, you need, if you have been assigned with this private IP address, your packet needs to be translated. Your address in the packet needs to be translated before the packet can go out to the internet. And this NAT mechanism is a short-term solution for IP address depletion. It was designed to be short-term, but now it's a long-term solution. So we all depend on that. But it also provides security for intranet service, saying that because within NAT you are invisible. So the good thing is that the outsider would not know what it looks like inside the intranet. Inside the intranet, it's invisible from the public internet. So it provides better security. And here's the example of NAT that it's the intranet inside and the internet here. So here are 2 hosts, and with sending a packet with the source of this and destination of this, source of this and destination of this. And when these 2 hosts are sending packet through the NAT to the public internet, their IP address and port number will be translated. See, their IP address are different, but they are private. So they need to be translated into public IP address. And here we got only one public IP address, which is this. So I do translation, but I need to because I have only one IP address, if I translated them into the same IP address, I would not be able to differentiate, or I would not be able to differentiate later on. So what I would do is that I need to do also port number translation. So I translate this port number into this. So if I have a packet coming in, if the NAT device has a packet coming in, it would look at this to see, okay, this is a packet destined to this or this. If it's destined to this, then it will be translated into this. But here again, you see, if I have a packet destination to this, I need to check the port number again. If the port number, destination port number is this, then I know I need to translate it back to this. For the others, for the port number other than this, I will translate it into this. So sometimes I need port number as well as IP address. IP address as well as port number in order to to differentiate them. And NAT will have a pool of global IP addresses, so that you would be able to allocate. But sometimes it only has one IP address. So in this case, you have more than one IP address. So you can allocate different IP address to different internal host. But if you don't, you would need translate a port number too. So I only have one IP address. So I need to use the port number to differentiate them. So I translate their port number into this, and this translation needs to be kept in the NAT table. Oh, sorry. Okay, I forgot to mention define the port number. The port number is the TCP port number or UDP port number, which is the address field in the TCP header or UDP header. In IP header, we have IP addresses as the address for the station, for the host, or the router, the address. Okay, but on a host, there might be multiple processes listening on the specific port number. So if I have a host with a multiple processes, I need to have a mechanism to differentiate them. And the way to differentiate them is to have them bind it to different port numbers. And that's called TCP port or UDP port. Again, the port number, I should mention that the port number is either TCP port or UDP port. And the idea of TCP port and UDP port will be covered in the next chapter, in chapter 5. But we bring out here is because if we do not talk about the port number, we will not be able to fully explain the idea of NAT, because it does need port number in order to differentiate different flows. Okay. but for the moment, let's just remember that, okay, the port number is either the TCP port or UDP port, and it's a mechanism for multiple processes on a single host machine. I mean, it's a mechanism to differentiate multiple processes on a single machine. If you have multiple processes running on top of a host machine, then you need port number to differentiate which process. And when we are talking about process, I'm talking about the program that run alive, the user program that run alive on the machine. So you have process running. So you might have client process or server process, and when they run, they need to bind themselves to a particular port number, either TCP or UDP port number, so that they got an address. They got an address on that machine, on that host. So you can view port number as an addressing scheme for the process. It's an addressing scheme. So if I'm a process, if I'm a host, I want to be uniquely identified worldwide. All I need is IP address, right? If I'm a host machine. But if I'm a process, a program process running on top of a host machine, and I want to be identified worldwide visible, then how can other people identify me? They will identify me by IP address, which is the host I'm running on top, and also the port number I'm binding to. So by IP address and port number, I could be identified worldwide uniquely. Okay, on NAT there is a particular, there are two particular usage application. One is the port redirection, and one is called transparent proxy. Suppose you have a web server, So you got an NAT device, but you got only one IP address, one real public IP address. So, but you want to have a web server, so the router has got a public IP address already. So you have no public IP address for your web server, right? So the web server itself, it's a host. The router got an IP address, but the host does not have a real IP address. So it will be allocated with a private IP address inside. But this web server needs to be visible worldwide, right? They need to be visible. But how do you make a host with private IP address visible to the internet? How? By this port redirect. So what you do is that you configure on the NAT, saying, okay, if there's a packet if there's a packet, if there's a packet sending to this destination, okay, this is my address. I mean, the address of the NAT, the public IP address of the NAT, but with port number 80, then it should be forwarded to this host with this port number. So this is the address. I mean, the private IP address located to the web server, and that web server is running on top of port number 8080. So I would, if I have receive a web request, HTTP request destined to this, then NAT would need to translate into this. Then it would forward to the web server inside. So in this way, if I configure this on the NAT device, and it would do this automatically, then it's essentially I'm making the web server inside, but visible to the internet. Visible to the internet. So all the internet station, an internet user who is accessing my web server, they would think that my IP address is 140.123.101.38. They would think my IP address is this, and my port number is 80. But in fact, my IP address is this. As a web server, my IP address is this, and I'm running on top of this port number. But on the internet, they would think my IP address and port number is this. And this is done by NAT translation. So this mapping is configured. I'm doing the mapping by manual configuration. I configure this, and then I'm making the web server visible to the internet. Another application of NAT is a so-called transparent proxy. That if I have inside, I have a client on the intranet trying to access the internet and to get some web page. But because my access line has limited bandwidth, so I have maintained a cache server, so that if the web request going out should be redirected to the the cache first, the proxy cache first. If the page is there, then they don't need to go out to get it. They can get it here from my cache. So that will save my bandwidth. So if I configure this, say all the traffic with destined to port number 80, they should be redirected to a cache, this one. So any request going to port 80 will be redirected to this. So all HTTP requests they'll be redirected to the internal proxy. So for this port redirection, it's a incoming request. I redirect. But for this, it's outgoing request. If it's outgoing, then I redirect to my proxy first. Okay. See, NAT implementation is very messy. Not because of the address translation. The address translation is easy. You translate the IP address and port number, which is easy. The difficult part comes from the cross-layer issue. Many application protocols or some control protocols, they put the IP address and port number in the message, protocol messages. So when you do the address translation, port number translation, you need to dig in into the application message to change the IP address and port number there. So let me take an example. In ICMP, this is the first example that you do the. Well, let's look at the basic part. You translate IP address and port number. So since IP address is in the IP header, so you need to recheck. You need to recalculate the IP header checksum. And since port number is in the TCP header, so you need to recalculate the TCP checksum too. So you need to recalculate the TCP and IP header checksum. And beyond that, if a protocol message contains IP address or port number, you need to dig in to modify, to translate them. So ICMP as an example, some ICMP packet will contain IP address. For example, destination unreachable, we will see this ICMP message. This message contains the IP address. So you need to go inside, dig in the message, and then translate the IP address there. Even though they are not in the IP header, you still need to change that. And ICMP is not the only example. There are many others. FTP is another example. In FTP, which we will see in chapter 6, the application layer, there's a protocol, FTP, file transfer protocol. And in the command, FTP command, it has IP address and port number. And worst of all, it's in ASCII. It's not in binary. See, if IP address is in ASCII, in binary, it will be 4 bytes, right? The 4-byte IP address. And the port number will be 2 bytes, as we will see in chapter 5. But if IP address is in ASCII, how many bytes would there be? See, this if this is in ASCII, how many bytes? 1, 2, 3, 4, 5, 6, 7, 8. 8 bytes. And this will be how many bytes? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Could be 14 bytes or 11 bytes. So when IP address is stored in ASCII, it's variable. It's variable. And it's not 4 bytes anymore. In binary, it's 4 bytes. In ASCII, it's not. So when you do the translation, when you go inside the FTP message to do the translation, the length, the packet size will be changed. If the new size is shorter, then you do what? You pad with 0, make it longer. If it becomes shorter, then make it longer by adding 0. If the new size is longer, then you can make it shorter. Now it becomes longer. Now you need to change the TCP sequence number in the TCP header, and this is covered in chapter 5. And then eventually you will need a table to do the mapping of the TCP sequence. So this makes NAT implementation difficult because of this. You might hide IP address and port number in application protocol messages. And application protocol messages are not binary. They are ASCII. And then translating the IP address and port number will modify the length. So that's a bad thing. And then you need to change the TCP sequence number, because TCP sequence number can identify each byte of the data. So it is for NAT to accommodate all applications. you need to implement a lot of stuff, and this make NAT implementation very messy. And this is called ALG, Application Specific Gateway, ALG.